Okay. So can you guys see my screen now? It says evolution.
Yes,
Yes,
sir.
sir.
Okay. Right. Yeah. Okay. So we'll now shift to the second part of the course, which traditionally starts after mid-sem, but as you know, we are a bit delayed this time. So the second part of the course is about evolution. Now, this is a topic that if you are studying biology, sometimes even if you are not studying biology, you can't really avoid this topic, right? Somewhere or the other, either in your classes or to some other thing, it always pops up now and then. So, what do you guys think about evolution? What is evolution supposed to do? What is it all about? Any quick answers?
Change?
Change?
Yeah, change.
So, when you, let's say, put a lot of vegetables in a pan and fry them and put some salt and turmeric in them and some other stuff, the raw vegetables change into a dish. That's a change. So, is it evolution?
Okay, no, I meant so change in the traits in a population. So given the way we defined population for the pop nine part.
Okay.
Could it be a slow and progressive change? I guess I don't know.
And progressing defined as?
Oh,
Yeah.
Selection of certain traits and elimination of others according to the situation.
Selection of certain traits and elimination of others according to the situation. So people who got more marks than a certain cutoff got selected into ICER Pune, others got eliminated. Evolution?
can we define evolution then?
Yeah. It can be done. It's just that if you do it the way you guys are doing, and the way you guys are doing is commonly how lay people do it. Okay. This is how most people who are reading a newspaper will end up doing it. If you do that, then the counter examples are too many. Okay. The one that comes closer to a formal definition is the one that somebody said, where you are talking about changes in the traits of a population. However, if you talk to most people, that's not how they see evolution. Okay, that's a very technical definition, probably coming from a person who has already been exposed to the topic for some time. But if you take a person who has not been exposed to the topic, typically they say how species originate. That's evolution. Okay. Now, obviously, this particular topic, or rather, evolution essentially comes from a certain observation that human beings have been making forever. So, explanandum, there are two terms, explanandum and explanans. Explanandum means that which needs to be explained, and explanans is that which forms the explanation. Okay. So, the explanandum of evolutionary biology is the observation that you take any biological, you know, animal or organism, whatever, you are going to see an enormous amount of diversity. Okay. And so, for example, here what I am showing you are a bunch of beetles, and just look at how much of variation you see in terms of their shape, their size, their color, finer details of their morphology. Yet, at some level, all these are recognizable as beetles. Okay, so that's one part. However, If we are talking about diversity, you can see diversity at many other places. You go to the seashore, you pick up a handful or a bucket full of sand, you bring those sands back to the you know laboratory, observe each grain under microscope, and you are going to see variation. You are going to see that each grain microscopically some way or the other is different from every other piece, every other grain. Yet the diversity that you see in biology or in living organisms is somewhat different from that kind of diversity, and the difference lies in the fact that that diversity that you see in the natural world, there doesn't seem to be a pattern to it. However, the diversity that you see in the living world, there seems to be a pattern. Okay, and it is because of the existence of this pattern. What is the pattern that you see? The pattern is that there are variation at every level, but yet you can group those organisms into what are known as nested hierarchies. Okay, what do I mean by that? So all humans, they have some difference from each other, which is why we can by and large tell one human apart from another. However, if you take all humans together, then in spite of all those differences, they will be distinguishable clearly from, let's say, a chimpanzee or a gorilla or an orangutan. Okay. However, now if you take humans and orangutans together, then they form another group, apes, which is different from, let's say, horses or cows or hippopotamus and so on. Interestingly, you now can take apes, horses, etc., etc., and now make another group called mammals, which will be very different from birds and reptiles and so on. So this kind of a nested hierarchy, it is possible to make that in biological organisms. It's not possible to make that in most non-living organisms. Now, obviously, there is a little bit of a trick over here. The trick is that if you measure sufficient number of parameters, then, and if you have a sufficiently creative taxonomist, then that person can create a tree out of anything. Okay, that's not the issue. The point is that these biological trees, you can make them in very different ways, taking into account very different kinds of characters, and yet you by and large end up getting the same tree again and again and again. Okay. However, that is not something that will necessarily happen, in fact almost guaranteed not to happen given the odds, for non-living organisms. So that is the sense in which the trees are not consistent in non-living things. It's not that you can't make them. You can of course always make them. So anyway, so this is the deal. A lot of diversity, but that diversity is not random, and this is what evolutionary biology has been trying to explain for a very, very long time. This is something that even the most ancient text of pretty much any civilization will always have some kind of an observation of this nature, and obviously most ancient texts turn to God to explain them. So what they did was they essentially said there was a God, and God created everything that we see around us, and the way in which that creation happened was slightly different. Some said 7 days, some said created out of whatever, some body part of something else, and so on and so forth. So one of the I mean, all these theories, obviously they are invoking God, and therefore once you invoke God in a theory, then there isn't much left to explain, right? One of the earliest theories of this kind was oh sorry, before we get into that, so we are, I mean, this particular course we are going to study evolution a bit formally. However, I realize that some of you may not have had biology in class 12. Specifically for those people, but also for those people who did have biology for in class 12, just way to refresh their memory. Here are 4 videos to which I have given you guys the link. These links are from, as you can see, a particular website called Stated Clearly. The problem with evolution is that there are millions of videos of those on YouTube, and many of those videos, unless they're coming from pretty good sources, many of those videos actually have, either they have clear misinformation or they have, let's say, stated wrongly. So this particular set of videos, I won't claim that they are completely free of mistakes, but at least when they make mistakes, their mistakes are of a fairly high order. They aren't low order mistakes. So these 4 videos on 4 topics of, bird's eye view on evolution, a bird's eye view of natural selection, why biologists believe that evolution has happened, and why it is important to study evolution both from an academic point of view as well as from an applied point of view. These are the 4 topics that are covered in these 4 videos. I won't cover them in the class, but I expect all of you to have a look at them. I don't anticipate that you guys will not understand anything in them. They are at a reasonable entry level, but in case there are anything that is not making sense, then get back to me. So let's start with a very, very brief history of evolutionary thought, and the emphasis is on the very part. Okay, people have written big fat books on how the evolutionary thought itself evolved across different cultures and over time and so on and so forth. So if we look at the Western world, then one of the earliest stabs at coming up with a theory for evolution was due to the early Greeks, like most things. So this is Plato and Aristotle as taken from Raphael's painting. And the way they conceptualized it is what is known as the typological theory. So what they said was that all organisms have been created as they are in their current form by the Lord, some mysterious form, whatever you call it, Lord, God, Zeus, whatever. And these organisms, you can actually arrange them in the form of a natural linear scale. This is what they call the scala naturae, or the natural scale. And this organization is in terms of complexity. And right at the lowest level, you have the non-living organisms, rock, soil, mud, etc. Higher than them are the plants, the trees, the grasses, and so on and so forth. Higher than them are the animals. And then right at the top, right at the pinnacle, are the human beings. So they suggested that each thing, each entity on this scale, they have what they call as their type, some kind of an essence. Okay. Now that essence, in some sense, you can think of it as the mean of the thing. However, when each organism is born and as it develops, it doesn't remain exactly true to the essence. There is some amount of deviation, a little bit here and there, from that essence. And that is what explains why, if you look at human beings, or for that matter any group of organisms, no two organisms within the same group are exactly identical to each other. Obviously, this doesn't explain the nested hierarchy bit, but then the way this was put was that's how God made them. So this way of thinking is no longer popular in evolutionary biology. However, there are several vestiges of this way of thinking which still pervades certain areas of science, if not explicitly, then at least implicitly. So for example, when even today in ecology, natural history, when you discover a new species, you know what you have to do? You have to collect a specimen and you have to deposit it in one of the few designated centers all over the world. And this specimen is what is known as the type specimen. Okay, the word type is essentially coming from this concept. And the idea is that every new thing that is collected, if you ask the question, is this, say, a guppy fish, or is this, say, a Siberian horse, then you actually have to send your new specimen to this place which holds the type, and that place will compare the type with whatever you have seen, and then they will say, yes, this is a whatever guppy, or no, this is not a guppy. So the comparison is still against a standard, and that entire conceptualization comes from this ancient Greek concept. The other thing that again comes from here is the concept of errors. So when you do experiments, you are always supposed to be very conscious about errors, right? Now, have you ever thought about it? Why in God's name is it called an error when you are trying your level best and putting everything in your power to make sure that there isn't any? So that those variations from reading to reading, most of the times those variations are real. Okay, those variations are there because some underlying condition here and there has slightly changed, because of which the actual measurement that you are doing is slightly altered. However, instead of calling that a variation in the reading, the moment you are calling it an error in your reading, you are essentially doing a hat tip to the ancient Greeks, wherein you had the concept that there is some kind of a true value, and everything else is every observed variation is a deviation from the true value. Yeah, somebody had something to say. Okay, so I'm telescoping about 2000 years worth of intellectual effort into nothingness, and then I'm straight away coming to the next important step in this. Okay, as I said, I'm not talking about a huge number of very important ideas that were put forth, but the next idea that is kind of still popular in the literature and lots of people are very enamored of it is due to this Frenchman called Jean-Baptiste Lamarck. Okay, so when you hear the name Lamarck and when you talk about Lamarckism, then what comes to your mind normally?
Giraffe.
Giraffe's long neck.
Right. So basically the concept of inheritance of acquired characters, right? So when the giraffe is trying to eat things at a taller and taller levels, its neck is getting elongated, and that is what is getting passed on to the next generation, which somebody's mic, I think, is making a lot of sound. Can you turn it off? Okay, so you automatically think in terms of this stuff, inheritance of acquired characters, and therefore by this you expect the son or daughter of a blacksmith to look like this, which typically obviously doesn't happen. Now, it's a very unfortunate thing that Lamarck's name gets associated with inheritance of acquired characters, because Lamarck's theory, the actual Lamarckism, was far, far, far beyond this. Okay, it was a full-fledged theory with 2 stages, okay, etc., etc. And Lamarck also realized that in order for a theory of evolution, he will need to have some kind of an explanation for how traits are passing from one generation to another. And Lamarck didn't really bother to come up with something new. All he did was he took what was the then common theory, most common and most widely accepted theory of inheritance, which was the inheritance of acquired character. And he's explicit about this. He doesn't claim any novelty for this part of the work. And unfortunately, this stuff is what gets slapped on into his name forever. So Lamarck's precise theory, the details of it doesn't really matter for our discussion. What matters is that this inheritance of acquired characters, we are reasonably confident that it doesn't work. or at least we were at some point. And therefore, the theory that really got traction was Darwin's theory of evolution through natural selection. And many of you might have seen this, caricature. So suppose you have both orange beetles and green beetles in the population, and for whatever reason the predators love the green beetles, and therefore the green beetles die at a much higher rate compared to the orange beetles. Therefore, the orange beetles will have a survival advantage, and they will end up leaving back a lot more number of offspring compared to the green beetles. And over time, these green beetles will be wiped out from the population, or their frequency will become very, very low. And the population will be, from a mixed population, will end up getting some kind of a, pure orange kind of a population. So this is what is evolution by natural selection. Okay. So although Darwin's theory is often just put in these words, in reality, Darwin's theory has a few more components. It's a bit more nuanced than what is simply presented over here. So one of the major ways in which Darwin changed the way evolutionary thinking was happening was by changing the focus of what needs to be studied. Till that point, evolutionary biologists, most of them, not all, but most of them, they were essentially trying to explain the diversity that exists. Okay. And that is why Lamarck came up with such a huge, elaborate stuff about how diversity exists. Prior to that, even the Greeks were talking about how you have an essence and there is random variation around that, and so on and so forth. Darwin actually slightly changes the focus. So Darwin ends up saying that, look, we don't really need to think about how the variation comes about. What we really need to focus on, in some sense, is the average, okay, is the overall property of the population, which most often is proxied by the mean, the arithmetic mean, but it can be proxied by some other kind of means also. But basically, we need to focus on some kind of a mean and take the variation as a given. Okay. So he essentially focuses this at the level of the population. Now, people have argued that Darwin is not the first guy doing this. Other people had done it earlier, etc., etc. Fair enough. We don't want to get into a historical precedence debate. But this is reasonably clear that it's Darwin's work which brings it, to the attention of people in a big. So what Darwin is saying is that, look, forget about what's happening at the level of each individual in the population. Look at the population itself. Okay. Each species, we know, has a bunch of local populations. And within each population, each individual will have some difference or the other from the other guy. Now, given this thing, this is the backdrop, Darwin has 4 or 5 tenets, and Darwin was amazing because when he was giving these tenets, he was very clear about where he was picking up each tenet from. So one of the things that Darwin observes is that, look, you take pretty much any organism on the planet, that organism will definitely end up producing more number of babies than what the environment will be able to sustain. Left to itself, the organism will end up producing more number of babies. This, in some sense, is analogous to the first law of population dynamics that we talked about, which is, if you leave an organism, howsoever slow breeder, if you leave it to itself, then sooner or later it is just going to overrun the entire planet. Okay. However, so this concept, he takes it from this guy called Malthus, who had proposed that populations, they grow geometrically, what today we call exponential. Then he made the observation that variation is there. You take any population anywhere, you have variation. This comes from his direct observations. This comes from observations by other naturalists, etc., etc., etc. But basically, he establishes clearly that individuals vary. Then he turns towards economics and says that if the populations are increasing at a fast pace and the resource base is not increasing at the same pace, or even maybe in some cases the resource base is not even increasing, then you are going to have resource limitation. Now, if you have resource limitation and all individuals are the same, there is zero difference between one individual and the other individual, then you don't expect much to happen. However, we have already established that not all individuals are the same. Some have one property and some have another property. Now, if it turns out that the properties, the traits that the organisms have, some of them will allow them to leave behind more offspring than the others. So suppose there is someone who has a longer horn, and by having that longer horn, it is able to defend itself better from the predators, and therefore is able to pass on more offspring. Is able to make more offspring for the next generation, contribute greater to the next generation compared to someone who has a short horn. And if the organism which has a long horn, its kids also have the long horn. Okay, it doesn't necessarily need to be as long as its parents, but in general, it tends to have longer horns than offspring of other guys. Then, if all these conditions are met, then this difference in reproductive output that we talked over here, okay, this is going to lead to changes in terms of the trait distribution across generation. Okay. Now, by itself, this is only saying how trait distributions will change when you go from one generation to another. However, remember, Darwin is trying to explain the origin of species. He is trying to explain how big ticket changes happen such that you end up getting what looks very, very different from that system. Now, that is something that is not going to be directly explained by this. Therefore, Darwin borrows one more concept, this time from the subject of geology. Okay. So there was this big guy called Charles Lyell in geology. This is the guy who gives the theory of continental drift. So he wait a second. I will have to check if Lyell is the guy who gives continental drift or not. I might be wrong on that one. But Lyell is the guy who talks about gradualism for sure. He is the person who says that even if changes are small, if those changes happen over a very, very long time, then small changes accumulated over a long time is equal to big changes. Okay. So this is what Darwin borrows from Lyell and says that these small changes, when accumulated over a long time, can lead to the evolution of new species, can lead to the creation of varieties which are so different from the original ones that for all practical purposes you call them a new species. Now, in this entire discussion, a very crucial component is what do we mean by a species? And this is a question that has been hotly debated for many years. However, when we come to Darwin was an amazingly clear thinker. So Darwin was very clear about what he means when he is talking about species. So his conceptualization was that there is, for pretty much every trait, you have a continuum. Okay. So all organisms are going to lie somewhere or the other on that continuum. And it is left to a human taxonomist to put a boundary somewhere and say whatever is on this side of the continuum is one species, whatever is on this side of the continuum is another species. So Darwin's conceptualization of species, which is also known as the morphospecies concept, is basically these are morphologically distinct groups as created by some competent taxonomy. So it was a very subjective kind of a definition. Now, there are obviously issues with anything subjective, and lots of people hate anything subjective, which and certain other considerations led Ernst Mayr to say that a species, basically is a group of organisms which is unable to exchange genes with another. Now, very interestingly, if you take that definition of species, what is known as the biological species concept, then whatever is said in the Darwinian theory, whatever is flashing on the screen right now, none of that says a word about how reproductive isolation happens. Therefore, if you take that definition of species, then origin of species doesn't say a word about origin of species. Okay, so this is something that is a source of a lot of amusement for lots of biologists, and the conundrum gets very trivially resolved when you appreciate that Darwin's conceptualization of species is different from the so-called biological concept of species. So the way Darwin framed this, he put a lot of emphasis on competition. Okay, however, it was made clear pretty soon that this entire thing is going to work even if you don't necessarily have this third point, that individuals are competing for limited resource. As long as you have variation, as long as some of that variation is inheritable, and as long as that variation is leading to differential reproduction, these three taken together is sufficient to ensure that there is going to be a change in the trait distribution going from generation whatever t to t+1, right? Now, to put the whole thing in a nutshell, if there is a variation within breeding groups, if at least part of the observed variation is inheritable, this is very important. If the tall guys are not breeding tall kids, then this is not going to work. So if at least part of the observed variation is inheritable, and some of the individuals are more successful in reproduction than others, and if this success in reproduction is related to this variation that you have, then if 4 of these conditions are met, then those with the most favorable phenotypes are going to increase in frequency in the population, and the population's composition is going to change, and evolution by natural selection will happen. Okay, very, very critical. Whatever I am defining over here is evolution by natural selection. As we are going to deal with, there are other forces also that can lead to evolution. Okay, there are other forces also that can change the trait distribution in a population. Not all of it is evolution by natural selection. So if that be the case, then why is it that we are so enamored of evolution by natural selection? What is it that that's so strong or special about the theory of natural selection? Natural selection is important because it explains one feature which is very commonly observed amongst most organisms, and that is the feature of adaptation. So if you look at organisms, if you look at the environment in which they find themselves, more often than not, you find a fantastic match between the properties of the organism, the traits of the organism, and the environment in which you will find it. So if you are in water, you will see that fishes have adaptations which make their life in water easier. If you look at organisms in desert, you will find that most of them will have some or the other adaptation which is very suited for the desert environment. Now, turns out that these other features or these other forces of evolution that we have, they can talk about change, but they cannot explain how the adaptedness of those traits can be explained. Natural selection explains it because what it is suggesting is that, remember, it is saying that if that trait is something that increases its reproductive success, and obviously the more suited you are to an environment, it is expected that your reproductive success is going to go up, and therefore it is in this sense that natural selection as a force is able to explain how adaptation arises. Now, there is something very peculiar to be observed over here. When you talk about natural selection, then the two most common phrases that come to your mind are A, survival of the fittest, and B, struggle for existence, right? I mean, these two are the signature phrases associated with evolutionary change. However, if you look at this thing, that is on the slide right now, you see that survival of the fittest is not really a necessary condition over here. The necessary condition is actually differential reproduction and inheritance of the trait that leads to that differential reproduction. That's about it. Okay. And that is going to happen even if there is no struggle for existence. Okay. Even if you have a condition where resources are not limiting, even then it is possible to have evolution by natural selection. That is why those two phrases are essentially relics of the past, which modern evolutionary biologists no longer use, although they permeate all kinds of other discipline literatures and of course the popular science literature. So, okay, let me just finish. So what happened because of this train of thoughts, bunch of things that Darwin put together? So what it said was that a species is not a constant unit. A species is something that can change over time, okay, as the population state distribution is changing and all those changes are getting accumulated. Now, this was a massive departure from the original Aristotelian thought that each species has a type and that type, that essence, remains unchanged over time, right? So this non-constancy of species was a big deal, although to be fair to Lamarck, for example, non-constancy of species is a highlight of his theory as well. So you cannot really give the credit for that to Darwin. More importantly, if you look at everything this way and then essentially extrapolate everything backwards, then you can say that probably life, the way we see it, has essentially descended from one or a few common ancestors, and then essentially there has been branching, of all kinds at all times. Now, if you think about evolution as a process like that, a branching descent with modification from common ancestors, then that also ends up explaining the property of the nested hierarchy that we had originally seen, right? And then, of course, Darwin proposed that evolution has to be a gradual process, and the relics of that is still evident today. As somebody said, evolution is a slow process. We now know that that is not always true. There are cases where within one generation you have a species getting formed, and this problem is actually arising from blindly taking that concept from geology and applying it to biology. We now know that microevolution and macroevolution, people are arguing they may not even be the same process. Okay, so according to this thought, macroevolution is simply microevolution integrated over a long time. But what now we are saying is that we don't even know if these two things are the same process or not. They may or may not. We'll talk about it a bit later. And this also obviously gives an explanation for why there is so much of diversity around us, apart from the fact that why they are nested. Natural selection comes about as a very strong mechanism for why all this is happening the way it is happening. As I have written in the bracket, that's not the only one, but one by and large accepts that this is probably the strongest of all the forces around. And it also establishes that evolution is basically a historical process. So whenever a branching is happening, remember in this particular case, he is basically talking about the fact that variation exists and then that variation is getting sorted through differential reproduction and inheritance. Okay. But there is also an element of stochasticity in the whole thing. Okay. So the way the sorting is happening, who survives, etc., chances also play a role in this. And therefore, the way life has branched into different branches, clades and all that, there is no guarantee that if you so-called replay the tape of life, you are going to get back exactly those branches. So there is a role of stochasticity, there is a role of noise at every step. And in fact, this particular question, what happens when we replay the tape of evolution? Under what conditions are the same changes going to repeat, and under what conditions are we going to get different lineages? This has been a very well studied question in evolutionary biology with some degree of nice answers, particularly in the context of bacterial evolution. So this, as you know, as soon as Darwin's views came in, people started criticizing it left and right. The single biggest criticism was, although inheritance was such a huge thing in Darwin's theory, Darwin could not give a good mechanism for inheritance. In the later editions, he gave the theory of pangenesis, the theory of the blending theory of evolution, which was basically that the offspring's character is going to be some intermediate between the two parents' character. However, as somebody showed it almost immediately, a very famous guy called Jenkins, that if that be the case, if the offspring is always an intermediate between the two parents, then all the variation very soon is going to converge or regress towards the mean of the population, and very soon there will be no variation left in the population. Natural selection will come to a halt. Okay, and if that were to be the case, obviously we have few billion years of evolution happening. You would not have had so much of diversity around. This was a massive problem, a massive headache for Darwin, which finally got resolved when Gregor Johann Mendel's work was rediscovered in 1900. Remember, his work was published in 1865, but people really took notice of it in 1900. Now, in that, Mendel actually ended up showing that the variation is not blending. Variation is particulate, and therefore, even if in a given generation a tall and a short plant will come together to breed a tall plant, the property of shortness doesn't really disappear and it can resurface in the next generation. So this was the spurt that was required for Darwin, or rather Darwin's theory. And once Mendel's and Darwin's theory got married to each other, life was very interesting. In what way life was interesting is something that we are going to take in the next class. So I'm going to stop right here. And yeah, I think I have run out of my time. So what I'll do is I'll stop the recording at this point, and if anybody is interested in asking any questions, etc., please hang back, and I will be happy to take care of this. Just once. Okay, Raghunandan, this has some special love for you. So this is again going into your drive. Are you there, Raghunandan dear? Wow.